Okay, this video is going to be a refresher in Newton's third law. Now, Newton's third law is one of the most famous laws in popular culture. Almost everybody knows it and everybody's heard of it. They're all like, oh yeah, you know, for every force there's an equal and opposite force. Yeah, man, I know physics, right? But the truth of the matter is, it is also one of the most misunderstood laws in all of physics. So let's dive in a little bit, okay? So Newton's third law says, and if you guys could go to the Newton's third law slide, it says there's an irrefutable rule of the universe, okay? And that rule is that all forces come in pairs. That for every force applied to an object, that object applies an equal and opposite force in return, okay? Now, let's look at this a little bit more closely, okay? So I'm going to give you a bunch of scenarios, and you guys are going to tell me which Newton's third law pairs exist between those two objects, okay? So remember, for every force applied to one object, that object applies an equal and opposite force in return, okay? So let's take the case of the Earth and the Moon, for example, okay? We have the Earth and the Moon, all right? Obviously, the Earth applies a force to the Moon, right? That's what keeps it in orbit, okay? There's a gravitational force there, right? Now, it turns out that the orbit happens because the moon's speed in this direction, the velocity in this direction, right, is so great that even though the moon's falling, it's still, you know, it's falling, but it's also then moving to this next position right here, right? So by falling, it's here instead of here, right? Which allows it to complete an orbit. But we'll talk more about that in circular motion. But the point of this is, if there is the Earth applying a force to the moon in that direction, okay, what is the Newton's third law pair? Well, the truth of the matter is the moon pulls on the Earth with an equal and opposite force, okay? These two forces, we'll call this F Earth, and this is F Moon. F Earth equals F Moon. Has to. This is what Newton's third law says. Now, I know you might be like, hey, I don't understand. Like, obviously, the Earth is so much bigger. How does it, you know, you know, it's not the Earth that's orbiting around the moon. Like help me understand this, right? So the bottom line is, yes, the Earth is a lot more massive, and we know from F equals ma, right, that if my mass goes up, right, for any given force, if my mass goes up, my acceleration goes down. So it appears as though the moon has less of an effect on the Earth, even though it's the same force, because the Earth is so much more massive, right? It's not going to affect the motion. The moon's not going to affect the motion of the Earth as much as the Earth is going to affect the motion of the moon. Okay, we're going to keep looking at these until they make sense. Okay, so what about this case where you have a kid in a chair, right? And he's sitting down on a chair. Okay. Now, obviously, the chair must be putting an upward force on the fellow. It's called a normal force, right? It's the force of the chair on the guy's butt, right? Okay. Obviously, otherwise he falls to the ground. That has to be true. But what is the Newton third law pair there? Well, the kid's butt is putting an equal and opposite force on the chair. So we'll just say force of butt, okay? So again, every time two objects are interacting with each other in some way, there is always going to be an equal and opposite force, okay? What about somebody just jumping up in the air? So we have somebody jumping over here, la-di-da-di-da, la-di-da-di-da. Oh my God, I am just the worst. Okay, so now you're not even on the ground anymore, so there's no normal force, right? But what is happening? You have gravity pulling down on this person, right? So that's going to be weight, right? But what is the Newton third law pair with that? Well, there's another object here, right? And that is the Earth. The Earth is sitting here below this person, right? And so if let's say this is me, if I jump, right, I am actually pulling up the Earth with an equal and opposite force to my weight. So if this is like, W1, then I'm pulling up with some W2 where W1 equals W2, okay? Guys, that's how important you are. That's how special you are. If you jump, you are actually pulling the Earth up. Now, again, you're like, no, how is this possible? How is this possible, right? Well, again, F equals ma, right? I'll just do it right here. So obviously, because your mass is so small, right, for any given force, that's going to be a pretty good acceleration, right? And as you know, that acceleration on the Earth is 9.8 meters per second squared for you, right? But if that same force is being applied to the Earth, which has just a huge mass, right, that means that the acceleration or the change in velocity of the Earth is equally tiny, right? Okay, so it appears as though you are not affecting the motion of the Earth at all in that process, okay? Because it is so tremendously more massive than you, right? Whereas, if you have two figure skaters who are around the same mass who push off each other, that change in velocity, that acceleration as they accelerate away from each other is about the same, okay? Only because their masses are comparable. Okay, we're going to do one more, and that is the case of a fellow pulling a rope, a tug of rope, okay? And so obviously the guy is applying a force to the rope, right? So there's like a force that he's applying to the rope, okay? What is the Newton's third law of pair? Well, it turns out that the rope is also pulling on his hand, right? There's an equal and opposite force of the rope applying a force to his hand. And we know this because if we do a tug of war, we actually have like rope burns, right? Like our hands feel kind of hot and worn out afterwards, right? And that is because the force is actually applying an equal and opposite. So I'll call this F1, I'll call this F2. And again, F1 has to equal F2, all right? So challenge yourself with this. If you're just driving your car, look at some place where you know that there's a force, right? It could be the force that your tires are applying to the road, or the force of a bird flapping in the air, and ask yourself, what is the Newton's third law pair there? Okay, if you see one force of something acting on something, what's then the opposite force of that thing acting on the other thing? Okay, now I told you there's a lot of misconceptions and confusions that come up with Newton's third law. Here's a big one. A lot of people will ask, hey, Scott, stop, pause. If this is true, then shouldn't all forces cancel? How can anything ever move if every force has an equal and opposite force? Okay? Take a second to see if you can answer that for yourself. All right? If everything has an equal and opposite force, if all forces come in equal and opposite pairs, how is it possible that anything even accelerates? How is it possible that we can actually change the motion of anything? Okay. If you look at every single one of these examples, all right, the forces, the opposite forces, are never applied to the same object, right? So, for example, if the Earth is pulling the moon this way, and the moon is pulling the Earth this way, it's not like the force of the moon is also on the moon, right? These equal and opposite forces aren't acting on the same object, so they're not going to cancel, right? The opposite force acts on the other object, right? So you never have to worry about forces actually canceling, all right? I hope that makes sense. For example, in this case, yes, the chair applies a normal force going upwards, right? But the opposite force isn't also applied to the kid on the chair. It's actually applied to the chair itself, right? So it's not like, this force on the boy is going to cancel out with his normal force. It's not how it works, okay? So Newton's third law pairs never act on the same objects. They act on the opposite objects, okay? All right, so I hope that's helpful. That is my little recap of Newton's third law. And if you have questions, reach out.